Power factor is the ratio of real power to apparent power in an alternating current circuit. It represents how efficiently the circuit is using the power it draws from the source. Power factor can range from 0 to 1. Displacement factor is a measure of the phase difference between the current and voltage in an alternating current circuit. It represents the amount of reactive power, which is power that does not do any useful work, in the circuit. Displacement factor can range from 0, which is a fully inductive circuit, to 1, which is a fully capacitive circuit. True power factor is a combination of power factor and displacement factor. It is a more accurate measure of the circuit's efficiency than either factor alone. True power factor can range from -1, a purely inductive circuit, to +1, a purely capacitive circuit. In a purely sinusoidal waveform, power factor equals displacement factor equals true power factor equals 1. This means that the circuit is using all the power it draws from the source efficiently, with no reactive power. However, if the waveform contains harmonics, which are distortions, power factor can be less than 1, even if displacement factor is 1. Power factor is a measure of real power versus apparent power, while displacement factor is a measure of phase difference. Power factor can only be positive, while displacement factor can be positive or negative. True power factor is a combination of power factor and displacement factor, providing a more complete measure of circuit efficiency. Now let's delve a little deeper into these concepts to provide a more comprehensive understanding. Considering power factor in more detail, it's crucial to remember that it's a dimensionless quantity. It expresses the ratio of the actual power being used in a circuit, measured in watts, to the apparent power, measured in volt-amps. A power factor of 1 indicates perfect efficiency, where all the supplied power is used for useful work. A power factor less than 1 signifies that a portion of the power is not being used effectively, leading to increased energy consumption and potentially higher utility bills. Common causes of a low power factor include inductive loads such as motors, transformers, and fluorescent lighting ballasts. These inductive loads create a lagging current, meaning the current waveform lags behind the voltage waveform, resulting in reactive power. Reactive power doesn't perform any real work but circulates between the source and the load, increasing the overall current in the system. Displacement factor, also known as the cosine phi, is specifically related to the phase angle between the voltage and current waveforms at the fundamental frequency. It's a direct indication of how much the current waveform is shifted in time relative to the voltage waveform. In a purely resistive circuit, the voltage and current are in phase, resulting in a displacement factor of 1. In a purely inductive circuit, the current lags the voltage by 90 degrees, resulting in a displacement factor of 0. In a purely capacitive circuit, the current leads the voltage by 90 degrees, also resulting in a displacement factor of 0, but with a leading power factor. True power factor takes into account the effects of both displacement and harmonics. Harmonics are distortions in the voltage or current waveform that occur at frequencies that are integer multiples of the fundamental frequency. These harmonics can be caused by nonlinear loads such as electronic devices, variable frequency drives, and switching power supplies. Harmonics contribute to a decrease in power factor because they increase the root mean square value of the current without increasing the real power. This results in a higher apparent power and, consequently, a lower power factor. The relationship between true power factor, displacement factor, and harmonic distortion is typically expressed as true power factor equals displacement factor times distortion factor. The distortion factor is a measure of the harmonic content in the waveform. Power factor correction is the process of improving the power factor of an electrical system. This is typically achieved by adding capacitors to the system to counteract the effects of inductive loads. Capacitors supply reactive power, which reduces the amount of reactive power that the source has to provide. This results in a lower overall current, a higher power factor, and reduced energy losses. There are several benefits to power factor correction. Firstly, it reduces energy costs. By improving the power factor, the overall current in the system is reduced, which leads to lower energy losses in the wiring and equipment. Secondly, it increases system capacity. By reducing the current, the existing electrical system can support more load without overloading. Thirdly, it improves voltage regulation. Power factor correction can help to stabilize the voltage at the load, which can improve the performance of sensitive equipment. Fourthly, it reduces harmonics. Capacitors can help to filter out harmonics, which can improve the power quality of the system. To illustrate with some examples, consider an industrial plant with a large number of motors. The motors are inductive loads that cause a low power factor. By installing power factor correction capacitors, the plant can improve its power factor and reduce its energy costs. Another example is a data center with a large number of electronic devices. The electronic devices are nonlinear loads that generate harmonics. By installing harmonic filters, the data center can reduce the harmonic distortion in its electrical system and improve its power quality. Regarding whether power factor can be 1 in a harmonic case, ideally, in a purely sinusoidal system without any harmonic distortion, the power factor is indeed equal to 1. This implies that the voltage and current are perfectly in phase and all the supplied power is effectively utilized. However, in real-world scenarios, harmonic distortion is almost always present to some degree. Nonlinear loads such as electronic devices, variable frequency drives, and switching power supplies introduce harmonic currents into the electrical system. These harmonic currents distort the sinusoidal waveform of the current, leading to a reduction in the power factor. Even if the displacement factor, which only considers the phase shift at the fundamental frequency, is close to 1, the presence of harmonics will still result in a power factor less than 1. The extent to which harmonics affect the power factor depends on the magnitude and frequency of the harmonic currents. Higher magnitude harmonics and harmonics closer to the fundamental frequency have a greater impact on the power factor. In conclusion, while a power factor of 1 is theoretically possible in a purely sinusoidal system, it is practically unattainable in systems with harmonic distortion. Harmonics inevitably reduce the power factor, even if the displacement factor is unity. Power factor correction techniques, including the use of capacitors and harmonic filters, are essential for mitigating the negative effects of harmonics and improving the overall efficiency of electrical systems. Let us consider the practical implications of these concepts further. Power factor and displacement factor are not merely theoretical constructs. They have significant practical implications for the design, operation, and efficiency of electrical power systems. Understanding these concepts is essential for electrical engineers, technicians, and anyone involved in the management of electrical energy. Firstly, a low power factor can lead to increased energy costs. Utility companies often charge industrial and commercial customers a penalty for low power factors. This is because a low power factor increases the overall current in the system, leading to higher energy losses in the transmission and distribution lines. By improving the power factor, customers can reduce their energy bills and avoid these penalties. Secondly, a low power factor can reduce the capacity of the electrical system. The electrical system is designed to deliver a certain amount of real power. However, if the power factor is low, the system must also supply a significant amount of reactive power. This reduces the amount of real power that the system can deliver, limiting the capacity of the system. By improving the power factor, the system can deliver more real power, increasing its capacity. Thirdly, a low power factor can cause voltage drops. When the current flows through the impedance of the electrical system, it causes a voltage drop. A low power factor increases the current, which increases the voltage drop. Excessive voltage drops can cause equipment to malfunction or operate inefficiently. By improving the power factor, the current is reduced, which reduces the voltage drop and improves the performance of equipment. Fourthly, harmonics can cause a variety of problems in electrical systems. Harmonics can cause overheating of equipment, such as transformers and motors. They can also cause malfunctioning of sensitive electronic equipment, such as computers and programmable logic controllers. Harmonics can also interfere with communication systems and cause inaccurate readings from metering equipment. By reducing harmonics, these problems can be avoided. Power factor correction and harmonic filtering are essential for maintaining the reliable and efficient operation of electrical power systems. There are various methods for improving power factor and reducing harmonics. Firstly, capacitor banks are the most common method for improving power factor. Capacitor banks are connected in parallel with inductive loads to supply reactive power. The capacitors counteract the effects of the inductive loads, increasing the power factor. Secondly, synchronous condensers are rotating machines that can supply or absorb reactive power. Synchronous condensers are typically used in large industrial facilities to provide power factor correction and voltage support. Thirdly, active power factor correction devices use power electronic converters to control the current waveform and improve the power factor. Active power factor correction devices can also reduce harmonics. Fourthly, harmonic filters are used to reduce harmonics in electrical systems. Harmonic filters are typically installed at the point where the harmonic currents are generated. Harmonic filters can be passive, consisting of inductors and capacitors, or active, using power electronic converters. The selection of the appropriate method for power factor correction and harmonic filtering depends on the specific characteristics of the electrical system and the nature of the loads. A thorough analysis of the system is necessary to determine the most effective and cost-efficient solution. In summary, power factor, displacement factor, and harmonics are important concepts in electrical power systems. Understanding these concepts is essential for ensuring the efficient and reliable operation of electrical equipment and reducing energy costs. Power factor correction and harmonic filtering are essential for mitigating the negative effects of low power factor and harmonics. By implementing appropriate power factor correction and harmonic filtering techniques, electrical systems can be optimized for performance and efficiency.